Okay, well, welcome to today's webinar on how heavier alternative fuel vehicles are expected to affect California pavements. My name is Mike Centetos. I'm the Policy Director for the UC Davis Institute of Transportation Studies SB1 Research Program. I'll be moderating the webinar today. Before we get into the presentation, I did just want to do a quick introduction. And Bernie, maybe you can share the slides when you're able to do that. So this webinar is hosted by the University of California Institute of Transportation Studies. UCITS is an expansive network of faculty, research and administrative staff, and students that are dedicated to advancing the state-of-the-art in transportation engineering, planning, and policy to benefit the residents of California, the nation, and the world. Established by the California legislature in 1947, the UCITS has branches at UC Berkeley, UC Davis, UC Irvine, and UCLA. The UCITS statewide transportation research program is supported by the state of California through funding from the Road Repair and Accountability Act of 2017, better known as Senate Bill 1, and the Public Transportation Account. Today's webinar will last an hour and 15 minutes. Bernie, maybe you could advance it one more slide. It will cover findings from a report requested by the state legislature through AB 2061 in 2018, which you'll hear more about in just a minute. You're going to hear from two of the report's authors today, Dr. John Harvey and Dr. Marshall Miller. Following the presentation, we'll open it up for Q&A. We'll ask you to please use the Q&A feature in the Zoom webinar platform. You'll see that little button at the bottom of your screen. Type in your questions at any point during the presentation, and we'll do our best to answer all of them at the end. We will be recording this webinar, and the recording will be available on the UCITS website. We'll make sure to put that link in the chat. So with that, let's jump into our presentation. The first presenter is going to be Dr. John Harvey. Dr. Harvey is a professor of civil and environmental engineering and the director of the UC Pavement Research Center at the University of California, Davis. And we'll then be hearing from Marshall Miller. And Dr. Miller is a senior development engineer at the Institute of Transportation Studies, also at UC Davis. So John, I will kick it over to you.
Thank you very much, Mike. Can you hear me?
Sound good, yep.
Okay. So a little background to this, the California truck fleet is changing, and as Marshall's going to talk about, changing rapidly, the directives to meet greenhouse gas emission goals. And that is the battery electric vehicles and fuel cell electric vehicles, and natural gas vehicles are being looked as a bridge technology or a transition technology. Right now, as of today, the battery electric, the fuel cell, and the natural gas vehicles are heavier than their corresponding diesel and gasoline counterparts. AB 2061 was signed into law in September 2018. It allows a 2,000-pound gross vehicle weight limit increase for near zero emission and zero emission vehicles. Near zero emission and zero emission, not meaning there's no emissions associated with them, but it's in terms of their propulsion, it's near zero or zero emission. AB 2061 increases the gross vehicle weight, but maintains current weight limits on individual axles. And when we get into the pavement part of this, we're going to learn a little bit about the interaction of gross vehicle weight versus axle weight. As a part of this legislation, UCITS was commissioned to study environmental impacts of law, as well as the effects on pavements and bridges. Next, please. So the objectives of the study we're presenting today were to estimate the effects on freight logistics of this implementation pathways for natural gas, fuel cell, and battery electric. We're calling these alternative fuel trucks in places, just to group those all together. To estimate the additional damage to local and state-owned government pavements caused by these trucks operating, well, what would happen with this increase in allowable gross vehicle weight of 500 to 2,000 pounds, to estimate the weight restriction problems for local and state government bridges, and to estimate the change in greenhouse gas emissions resulting from implementing these vehicle fleet changes, considering both the well-to-wheel vehicle emissions, meaning including creation of the energy that propels them, as well as the use of that energy, and also considering the greenhouse gas emissions of potentially increased pavement maintenance and rehabilitation because of the increased weights of these technologies. Next, please. So the research approach we took, and there were a lot of dots to connect here, and a lot of different areas of analysis. The first was to estimate the additional weight of these new technology vehicles and the resultant changes in well-to-wheel carbon emissions, considering 3 alternative pathways for implementation, um, 3 major categories of truck, 2 heavy-duty truck types, long-haul and short-haul heavy-duty tractors combinations, and medium-duty urban trucks. And this was looked at, we looked at 3 milestones, 2020, 2030, and 2050, and we interpolated in between those. As a part of this study, we also estimated the growth in truck travel and where the increased travel of new technology trucks would be likely to occur, using projections from the California statewide travel demand model, and based on changes in light, medium, and heavy duty truck miles traveled. Note that those definitions are much broader. What's covered in the CSTDM is a lot more trucks going down to the light duty trucks than are covered in our study, the major part of our study. Then to assess the impacts of the axle load changes on bridge deterioration and cost, using the best available information we had within our scope and budget, which was a US DOT comprehensive truck size and weight limits study. Mechanistic analysis for bridge damage is not available. Next, please. Then we're estimating the changes in truck axle load spectra for the different implementation pathways using Caltrans weigh and motion data from state highways, which is we use UCPRC uses it for a number of different purposes for Caltrans. We estimated city and county road spectra from portions of the state highway spectra for similar type roads. We assumed residential street spectra, considering that they only really carry waste collection vehicles in terms of heavy vehicles. Looking at that, and they don't really carry the really big package delivery trucks much anymore. We assessed greenhouse gas and cost impacts of the change in pavement deterioration that we modeled from the axle load spectra changes that we modeled for the 3 implementation pathways. And to do this, we use mechanistic empirical pavement analysis to simulate the pavement damage. And we use the 2 programs that Caltrans uses for pavement design and analysis, CalMe for asphalt pavement and Pavement ME for concrete pavement. And then we did conceptual level estimates of the increased pavement cost based on the incremental pavement damage for 6 representative pavement scenarios. We also calculated the greenhouse gas for those scenarios. And then the results for the entire period of 2020 to 2050 were interpolated from the results from 2020, 2030, and 2050. And then we prepared an overall summary. So that's kind of a big overview of the project and the approach taken. And I'm going to hand it over to Marshall to talk about the pathways in the vehicles.
Thanks, John. Okay, so I just want to give sort of an introduction to the technologies and some of our methodologies for the part that I was involved in. ZEV technologies, and I'm going to focus just on the ZEVs, not on the natural gas, because they play a much smaller role. ZEV technologies emit 0 tailpipe emissions, but there are possible upstream emissions from the production and delivery of fuels. For example, natural gas power plant will produce electricity, and there could be greenhouse gas emissions from that power plant, and electricity produced from that power plant used to produce hydrogen will also have upstream emissions for the production of hydrogen. Those emissions for both hydrogen and electricity are expected to become less over time. The state has required more renewable hydrogen and electricity production. And in fact, in our study, we assume the emissions go to zero, fully renewable systems by 2050. Back up, please. Okay. Batteries, pretty much everyone's familiar with. You have them in your car. They are energy storage systems. That means that in order to have more energy in them to produce a greater range for a battery electric truck, you require a larger battery and a heavier battery. Batteries for battery electric vehicles include additional things like battery management system, which monitors voltage, state of charge, etc., and a thermal management system, which keeps the battery operating in an appropriate temperature range. Fuel cells are also electrical devices. They provide electrical power to power electronics, which drive the motors, and in that way, they're similar to batteries. But they're not energy storage systems, they're an energy conversion system, much like an engine. There's a separate fuel tank for both conventional vehicles and fuel cell vehicles, and that fuel tank supplies fuel to the engine or the fuel cell. Greater range for a fuel cell vehicle only requires expanding the fuel tank. The fuel cell itself would essentially remain the same size and weight. Okay, next slide. So there are three truck types that we looked at for the study: long-haul tractors, short-haul tractors, and medium-duty urban trucks. Long-haul tractors are generally Class 8 tractors. They travel a very long distance per year. Vehicle miles traveled, something like 100,000, could be a little lower or significantly higher. Generally, they do not return to base to fuel. Pictures are on the right there. The top one is of a long-haul tractor. Short-haul tractors can be heavy-duty Class 7 or 8 tractors. They typically travel locally or regionally. They often return to base to fuel. And medium-duty urban trucks for this study typically, or an example would be a box delivery truck. They're Class 4 to 6, and examples might be a FedEx or a UPS truck. Next slide. So the methodology we use to estimate truck weights starts with diesel trucks. Essentially, we look at new technology truck weights, battery electric or fuel cell, relative to the weight of a diesel truck. Looking at the diesel truck, we consider the components that would be removed from a diesel truck in order for a battery electric or fuel cell truck. And those components are the engine, fuel tank after treatment, and the diesel exhaust fluid tank. The major new components that would be added for a ZEV truck for battery electric would be the battery, the power electronics, which would include motors. The fuel cell electric vehicle would include fuel cell, a battery. Typically, fuel cells would have hybrid operations, so they would include a battery. Power electronics, again, including a motor, and the hydrogen storage tank. Now, for these battery electric and fuel cell vehicles, the component weights are assumed to decrease with time due to advances in technology. We've already seen that batteries and fuel cells have increased power and energy density over the past decade or so, and that is assumed to continue out to 2030 and then to 2050. There could be lighter weight materials, but the overall weight reduction can be fairly significant. Next slide. Okay, the diesel truck component weights that we looked at to be removed are shown here. Basically, we picked a particular engine from a long-haul and short-haul tractor and from medium-duty urban truck, and we looked at those components, fuel tank and after treatment and so on. And this is in kilograms, the weights that would be removed from a diesel truck, not part of a battery electric or fuel cell truck. Next slide. So this, sorry, the last slide, the one before. Next slide. There, thank you. This shows the battery electric truck weights, the components and the total weight for the three truck types, long haul, short haul, and medium duty urban for 2 years, 2030 and 2050. And you'll notice in the second column, For the long haul and short haul, the range of these trucks increases over time. And that's because the battery is especially heavy. And so in 2030, we assumed a smaller battery that would give a smaller range. And given that the battery energy density we expected to increase over time, we extended the range in 2050. But you still see the battery weights decrease from 2030 to 2050, even though the range is increasing. And again, that's due to the increased energy density of the battery. The power electronics typically stay the same. And the last column shows the total extra weight of the truck over a diesel truck in pounds. The reason we use pounds is that you can compare it to this 2,000 pound exemption. You can see that for long haul, there's a very significant increase in weight. And that's one reason why some people think that long haul will not have significant market, battery electric long haul will not have significant market penetration compared to fuel cells. Short haul extra truck weight does decrease significantly and does fall below the 2,000 pound exemption. And then you see medium duty urban also falling significantly from 2030 to 2050. Incidentally, all of these slides we show in the report what table they're taken from. So you can see in this one that it's this information is from table 2.3. Next slide. So this is the same table for fuel cell, again, for the 3 truck types in the 2 years, 2030 and 2050. Second column, you see significant reduction in the mass of the fuel cell itself. The last column shows the total extra weight. Again, this is in pounds, and it's significantly lower in extra weight than battery electric trucks. The long haul in 2030 would be just slightly over the 2,000 pound exemption, but would fall under it in 2050. For short haul in 2050, we actually show a weight reduction with the assumptions we made. Medium duty urban, again, you see a weight reduction from 2030 to 2050. Next slide. Okay. So here I'll talk about the methodology for determining the vehicle stock, the number of battery electric and fuel cell vehicles on the road in 2030 and 2050. We use a model called the Transportation Transitions Model that we developed. It's a stock turnover model. There are 8 truck and bus vehicle types, including long haul, tractor, short haul, medium duty urban. We have scenarios that are driven by sales shares for various vehicle and technology types. So each year, we have a percentage of overall sales for a particular vehicle and a particular technology. So 2020, there's a percentage of fuel cell long haul trucks. 2030, a percentage of battery electric long haul trucks, diesel long haul trucks, fuel cell long haul trucks, and so on. Now, the scenarios we used are based on the original projections from CARB of their advanced clean truck regulation. Unfortunately, or kind of necessarily, that regulation, those projections going to the final regulation were increased significantly after our study was done. The table on the right shows the regulation percentage of ZEV sales for 3 classes, class 2B and 3, class 4 to 8, and class 7 and 8 tractors for 2 model years, 2030 and 2050. The original regulation required sales to start in 2024. And for 2030, for class 2B and 3 and class 7 and 8 tractors, required 15% of sales to be ZEVs in 2030. The later regulation, the final regulation, increased that to 30%. So that's quite a significant increase. The later regulation also added requirements in 2035, and those are shown there, 55% for class 2B and 3, 75 for class 48, and 40 for class 7, 8, and tractor. Now there's a further wrinkle. Just earlier last year, a few months ago, Governor Newsom released an executive order that actually requires 100% of on-road vehicles, at least wherever possible, to be ZEVs by 2045. And that's even more aggressive than the new advanced clean truck regulation. So I'll talk about the differences in what we did for our study and what might be required by that executive order in the next slide. There are three scenarios: low, baseline, and high. The baseline basically followed the Act regulation, and by 2050 had 100% short haul and 100% medium duty ZEV sales. For long haul, that was 80%. The low scenario is about half of that, and the high scenario is roughly 50% larger. So this slide shows the actual vehicle stocks for the three truck types and three scenarios. The first line, LH, is long haul, 1 is high, 2 is baseline, 3 is low. So you three scenarios for the three truck types. I'll focus on year 2025. That's the last three columns. That total shows the total number of stock of the different vehicle types. The BEV, battery electric and fuel cell FC, shows the stock of battery electric and fuel cell for each of those truck types for each of the scenarios. So one thing, in 2030, we assumed that battery electric vehicles would sort of dominate market penetration over fuel cell. But by 2050, in general, fuel cell typically caught up. For long haul, fuel cell, for long haul, we assume that fuel cell dominates. And that's because of the reason that I mentioned, that for battery electric trucks, the batteries for long haul are excessively massive and probably would require, would be problematic for market penetration. So fuel cells dominate in long haul. Typically by 2050, fuel cells and battery electric with this set of assumptions are roughly equal in stock by 2050. One quick thing to notice is for long haul, if you look at the top line, even for our high scenario, the sum of battery electric and fuel cell is still significantly less than the total. And that's because we took the original ARB Act regulation. Those numbers would have to increase to meet the governor's executive order. So there would, if we actually can meet that executive order, which isn't certain, the number of long haul trucks would be higher for ZEVs. Short haul and medium duty in the high scenario are roughly or equal to the total number of stocks. So the difference really is in long haul. Next slide. So here's the methodology for estimating carbon emissions. Our TTM model includes fuel economy by vehicle type, technology, and model year. We include vehicle miles traveled by vehicle type and model year. As vehicles get older, they typically travel less miles. From those two, we can calculate the fuel use for the entire fleet for each fuel for each year. Then for each fuel, we have the fuel carbon intensity, which is the well-to-wheel greenhouse gas emissions in grams per CO2 equivalent per megajoule, for example. Using that, we can calculate the total greenhouse gas emissions every year for each fuel type, for the total fleet, and for each vehicle type. The assumptions we made, as I mentioned, for hydrogen and electricity, we assume the carbon intensity will go to 0, meaning 100% renewable production by 2050. For diesel blends, we assume they will stay constant from 2020 through the end of the study, 2050, and that blend is roughly 16% biomass-based diesel. The scenarios, we did have a business as usual scenario, which assumed a very small market penetration of ZEVs through 2050, and then we had our low, baseline, and high market penetration. Next slide. So this shows carbon emissions for each of the scenarios, including the BAU, for 2020, 2030, and 2050. It shows total and the percent reduction from the BAU. If you notice in the BAU, the total is going down from 2020 through 2050. That's due to two things. One is significant improvements in conventional diesel truck fuel economy. In addition, there is some penetration of natural gas and smaller penetration of ZEVs into the BAU scenario, and that reduces the overall carbon emissions. If you look at the baseline, high, and low for 2030, the percent reductions are fairly modest. Basically, that's that there just aren't enough trucks in the stock by 2030 to reduce emissions by very much. By 2050, you start to see very significant emissions reductions. For the high, the reduction is 87%. Remember, the governor's executive order actually wants a target of net zero emissions by 2045. Because of the assumptions and the timeline of our scenario, we do not have that in our results, but the high scenario is still a fairly significant reduction in carbon emissions. Even the baseline is a fairly significant reduction in carbon emissions. Okay, so I'm now going to turn it back over to John to finish the talk. So we'll go to the next slide and John can start.
Thank you, Marshall. The first chapter 2 or chapter 3 in the report is estimating freight flows in California. This work was done primarily by Professor Miguel Heyer at UC Davis. So he used the results from the California statewide travel demand model to estimate freight flows. He looked at different intervals in time up to 2040 is as far as he could go with that model. Again, to note, that model considers light duty as well as medium duty and heavy duty trucks. And those don't match up the trucks that Marshall was just talking about. Marshall's talking about the heavy duty trucks and then a portion of the what's called medium duty trucks in the CSTDM. So this gave us more of a qualitative sense of increases. So the other thing that we did is in this was trying to look at growth in different sectors of the state road network. CSTDM uses signalized speed limits for passenger vehicles to classify road types. Lower volume urban roads will have lower speed limits, freeways will have higher speed limits, and so on. The main takeaway from this was that 11 out of 58 counties are expected to receive about 75% of the truck VMT in the state up to 2040, with the percentages not really changing in each year according to the model. And that the market penetration of the zero emission vehicles is expected to follow a similar distribution. So where the trucks are now is where the main penetration is going to be, and 11 of the counties, and they're listed in the report, carry about 75% of the truck VMT. Next, please. We tried to look at bridges, and the best source that without trying to develop our own mechanistic models of stresses and strains and how they fatigue the concrete and so on, we went to the MAP 21 comprehensive truck size and weight limit study. This provided an estimate of $0.4 billion nationwide for one-time costs to strengthen and replace bridges due to a 5-axle 88,000-pound gross vehicle truck. AB 2061 is looking at a 82,000-pound truck. So what we had to do was some very gross top-down conceptual estimates. The main takeaway from the US DOT study, they couldn't come up with a much better estimate either. And their statement was that research and data are not advanced enough to enable the US DOT to say when or even whether it will be in a position to collect and analyze better data and apply it to improve policy determinations and regulatory strategies. Their main takeaway was think about not increasing gross vehicle weights because we don't think we can analyze what the effects are on bridges. Next slide, please. Again, as I said, we did the best we could. We took a top-down first order calculation to translate the national level cost to California. We looked at the bridge categories in that study and looked at the structurally deficient category. California, according to that study, has about 6.2% of all bridges in the US that are structurally deficient, and about 3.9% of all structurally deficient bridges on the national highway system. National highway system bridges are longer and more costly to update. We just split the difference between those, assumed that about 4.5% of California bridges are structurally deficient. We then prorated conservatively what their cost estimate was for an 88,000-pound truck and applied it to an 82,000 pound truck and did the very simple equation you can see there. And it came back with a very, very low amount of dollars in 2011 dollars, which was their baseline. We don't know. That was the best we could do with what we have, with the largest caveats that we can hang on that number, because they just didn't seem to have an ability to go there. This cost estimate does not include increased annual maintenance costs due to heavier trucks. This is really just about upgrading. That number seems very low to us, but that's the best we could see. Okay, next slide. So now switching to pavements, the first step that we had to make was we had to estimate, use the information that Marshall was showing for truck weights and their distribution across axles for different types of trucks, different propulsion systems in different years, and apply those to what we call axle load spectra. An axle load spectrum is a table showing the distribution of axle types, and we typically divide those up into steering, single, tandem, and tridem. And then what's the percentage of different loads within each axle type within a population of trucks. The data that we used is that Caltrans operates 132 weigh and motion stations at key highway locations across the state. That's far more than any other state has got. We collect, process, and store that data. These weigh and motions collects, process, and store that data on truck traffic, including truck classifications, speeds, gross vehicle weights, and most important for pavement damage is axle loads, not gross vehicle weights. The UCPRC periodically downloads this data, updates the spectra, which we use which Caltrans uses in the pavement management system and in the concrete and asphalt pavement simulation and design programs. We've taken all the spectra across the 132 stations, and we've boiled those down into 5 typical patterns of axle load distributions, from 1 being the lightest and spectra 4 and 5 being the heaviest and the most damage. In the analysis that we did, we assumed that local roads, county roads, and those city roads that carry trucks have the lightest spectrum, and that kind of matches up some more qualitative information that we have. Just a caveat that's not in the report is that overall, when we've looked at axle loads spectra across the period of 2005 to 2015, overall axle loads are generally getting a little bit lighter. The main thing that's increasing pavement damage is that the numbers of truck passes are increasing. Axle loads are about the same or slightly lighter in general for conventional vehicles in the current fleet over the last 10 years, but the numbers of truck passes are increasing considerably. Next slide, please. So we then took the baseline numbers and the pathways that Marshall had developed, and we took the distributions across the tractor of the long haul and short haul trucks and across the medium duty trucks. So we looked at the 3 truck types, 3 alternative truck technologies, and their market penetration from Marshall, and then the 3 scenarios that he talked about for pathways to implementation. We then have to convert those into 24-hour. We actually have to look at an axle load spectrum for every hour of 24 hours because including the numbers of trucks as well as the axle load distributions, because the temperature of the asphalt at the time that the truck hits it has an impact on damage. Asphalt is stiffer at cold temperature in the night and weaker in the day. And temperature also affects concrete pavement with regard to how much it's changing its shape when the top gets hotter or the top gets colder than the bottom. So if we look over on the right-hand side there, we can see the 5 spectra, typical spectra, and these are averaged for all of the stations in the state WIM network are grouped into one of these 5 spectra. And the x-axis, the horizontal axis on each of these 5 spectra, is the load on the axles converted into as if they're a single axle. So if we have a tandem axle, which is 2 axles spaced closely together, we take the tandem axle weight and divide it in half, and that gives us the equivalent of single axles. What we can see is that the light spectrum, you can see each of the different axle types with the 3 colors, the green, blue, and the red. Single steering, tandem, and you can see tridem. We have very few tridems. That's the purple line. So most of our axles are the steering single, a single axle, or a tandem axle, 2 singles closely together. And then the black line in each of these plots is the, if we take all of those equivalent single axles and group them together, this gives you an idea of the loading in each of the spectrum. So if we look at spectrum 1, our lightest, the highest peak and most of the axles are actually very low. They're skewed to the left. And then as we move to spectra 2, it starts to move out to the right. Spectrum 3 moves out to the right further. And then when we get to spectrum 4 and 5, those have quite a few heavy axles, which are farther to the right here. But we still have significant numbers of unloaded axles, which are the ones on the left, and partially loaded axles, which are the ones in the middle. So that's a brief look. So our axle load spectrum is where we need to take the data that Marshall gave us and then apply it and update these axle load spectra for each of the pathways of market penetration of the alternative fuel technologies for 2030 and 2050. Next slide, please. So the result of this, and we'll explain why, we had an idea when Marshall gave us, we walked through the data that Marshall gave us, and we began to look at it. The answer was that we see very small changes in 2030 in the axle load spectra and very small changes in 2050. And the question is why? These trucks are heavier than the diesel and the gasoline in 2030. But as Marshall was showing, there's some projected significant weight reductions by 2050. So this is our overall statewide average tandem distribution. I'll note on here that the legal load in California is 34,000 pounds, which is right about here. So we have far fewer overloaded axle loads, not vehicles, overloaded axles in California compared to some other states. We don't carry as much heavy cargo, and probably relates to enforcement as well. But on this graph, the 2020 baseline, the 2030, and the 2050 projections, each of those axle load spectra are shown on here, averaged over the entire state. And what you can see here is you can't see any difference. Those differences are so small that they're almost non-existent. So why is that? And we'll come to that reason why. Well, I'll tell you why right now, and then I'll summarize it in the summary. The reason is because the market penetration is so small in 2030 when the vehicles are heavier than the current vehicles. And then when we get to as we move towards 2050, market penetration is increasing significantly, but according to the projections and interpolating those projections, the vehicles are getting lighter, and in some of the axles are getting lighter than the current conventional vehicles, and some of them are getting a little bit heavier. But the overall net result is that there's just not that much change. The other thing that's going on here is that the only changes are on the tractors, the part of the truck that pulls the trailer. The trailer axle loads we don't expect to change because the axle loads didn't change. So they can't shift weight back to the back of the truck onto the back axle if they're at the limit already. unless they want to get caught and pay a fine. So that's the basic reason that we saw why we saw so little difference in the axle load distributions. Next, please. So we then took those truck weights and we ran pavement analyses, and then we ran life cycle assessment for the material production, the transportation to the site of the materials, and the construction activities, and looked at what the changes in the spectra would do to the damage to the pavements, and then how that would change the expected sequence of rehabilitation of these pavements. So we looked at the materials transport, construction, and the primarily the rehabilitation of these pavements. The system boundary did not include the use stage. We didn't look at truck pavement interaction, any of those things, and the routine maintenance activities. Again, because the damage levels were so low, and many of our maintenance activities are primarily related to dealing with what we call age-related cracking, how the pavement deteriorates under changes of temperature and rainfall and solar radiation and so on. So we focused on the rehabilitation. For the end of life stage, we assumed that the old materials were removed in the case of concrete, or milled in the case of asphalt, and then transported to a plant for recycling. Nearly all pavement demolition is recycled back into pavement in one way or another. Next, please. So there's a detailed modeling approach shown in the report. To summarize it, we developed example rehabilitation treatments for pavements for each category of pavement analyzed. Different types of state highway pavement, county roads, major urban roads, and then residential streets for the main study, and residential streets and the road into the waste handling facility, the landfill, for the natural gas vehicles. With those changes in spectra, we use CalMe and Pavement ME to calculate the damage. From the damage, we looked at the change in the distresses and then figured out the resulting changes, and then converted those into costs over the life cycle using a top-down conceptual approach, and then did the same thing with the greenhouse gas emissions over the life cycle. We used well, I'll come to the details in that. So the results from the example pavements were then applied to, extrapolated across the state and local network pavement categories to get the final state sum. And again, as I mentioned, we did a special case look at natural gas waste hauling trucks for residential streets and for waste disposal access roads. Next, please. So the factorial, just to go over it again, business as usual, using 2020 trucks, the 3 market penetration cases, which we analyzed for 2030 and 2050 spectra. For each of those axle load spectra and each of those cases, we did what would have been the previous treatment, and then looked at the change in life of that treatment with the changed axle load spectrum. We used a 20-year rehab design life for the state highways, and approximately a 12-year service life for design life for the local government pavements. We analyzed each of those, as I said, and calculated change in pavement life attributable to the axle load changes, and then assumed also that whatever that previous treatment was, the initial treatment, we were just looking at the timing of repeating that treatment. And if there's more damage and that rehab has to happen sooner, that's going to then increase the life cycle cost and the greenhouse gas emissions, because it has to be done more frequently. Next, please. The results from those 7 AFT implementation scenarios were applied to state highways with asphalt surfaces, and we then analyzed asphalt pavements, typical asphalt pavements within each of the 5 axle load spectra, from the state highways that are carrying light truck traffic up to the state highways that are carrying the heaviest traffic. We then looked at state highways with concrete surfaces and typical pavement structures in each of those. with the 3 heaviest axle load spectra. The concrete roads tend to be on the heavier trafficked roads. We looked at asphalt surfaced urban major and arterial streets, well, as one case with the lightest axle load spectrum. And then we looked at a rural major or county road with the lightest axle load spectrum. We looked at the natural gas vehicles with a 500-pound tank, a smaller vehicle, and then up to the 2,000 pounds. And I looked at that on an asphalt surface residential street and on an asphalt surface waste facility access road. We took those results from each of those and then looked across the amount of lane miles in the state road network. And on the right-hand side, I have a graph from the local streets and roads report from 2018. We can see that 45% of the lane miles in the state belong to the cities, 35% belong to the counties, and 13% belong to the state, Caltrans. In terms of vehicle miles traveled, it's about 45% state and 55% cities and counties. For our costs and our greenhouse gas emissions, we're looking at the lane miles. Next, please. So once we'd seen the changes in the axle load spectra, we didn't know exactly the answer, but we were not completely surprised that because of those implementation pathways and how fast implementation occurs and the expected projected changes in the tractor weights and the medium duty truck axle weights, the mechanistic analysis showed really no discernible difference in the expected pavement performance, very small, 0 to 1% increase in damage. The damage, again, is limited in part because pavement damage is driven by the very heaviest axle loads. Pavement damage is not driven by gross vehicle weight. And AB 2061 doesn't allow axle weights to increase. The other thing is, as I was mentioning, axle weights are not going up from what we can see on the state highway network over the last 10 years. And as we just saw for the tandems, there's not that many axles that are at or above the current axle load limits. A lot of trucks, the way our economy works, a lot of our trucks are running empty or with very light loads, partial loads. It's really only on a few of the long haul corridors, I-5 in particular, a couple other just major truck routes where we see significant numbers of trucks running loaded both ways. So if trucks, for example, are running empty one direction and loaded the other direction, and the loaded condition doesn't even necessarily push them up to the axle load limits, and those aren't growing, then these changes from the ZEV vehicles are just not that large. And again, we don't anticipate much in the way of changes in the tractor axles. It's in the trailer axles. It's the tractor axles on the segmented trucks that have the changes. So the trailer axles not changing very much also dilutes the effect of these axle load changes on the total pavement damage. Just a little primer on this, the basic background, and I won't spend too much time on this, but pavement damage follows very, very, very roughly what we call the fourth power law. And what that says is that pavement damage approximately changes with the axle loads raised to the power 4. So a doubling of axle load doesn't double our pavement damage. A doubling of axle loads increases our pavement damage 2 to the 4th power, or 16 times. Similarly, having our axle loads doesn't have our pavement damage, cut it in half, it decreases it by a factor of 16. So if we half the axle load actually causes, reduces the damage by 94%. So when we're looking at pavement damage, we're only looking at the heaviest axle loads in the spectra, which cause the most damage. For this reason, when we design pavements, we don't design them. We completely ignore the cars. We ignore the light duty trucks. And really the empty and partial loaded vehicles do not cause that much damage. So a little bit of an increase here and there on the tractor axles and on the axles on the medium duty trucks just don't seem to cause that much damage, according to the analysis that we did. Next slide, please. Taking a look at the minor streets and waste hauling roads, in general, our residential streets primarily fail not due to the waste trucks and not due to any vehicle loading. Most of our residential streets fail because of aging of the asphalt. And as the asphalt is exposed to heat and air over time, it becomes stiffer and it can't handle day to night and winter to summer temperature changes. And most of our cracking on residential streets occurs because of aging and environmental exposure, not the vehicles. So we analyzed for the residential streets a typical 3 inches of conventional asphalt on 6 inches of aggregate base, pretty classic 3-on-6 residential street. And we found that the existing pavement didn't fail under the existing waste trucks. And again, we modeled the trucks start their run empty, they fill up as they work through their rounds, and then the last street that they're operating on, they're full, and then they head back. So we accounted for starting empty and getting full at the end of each round and then heading back to the waste facility, handling facility to empty. So when we increased the axle loads on the natural gas vehicles, waste trucks, we found that they still didn't fail by truck loading. They still failed by environmental loading. And again, part of the reason is for that is AB 2061 does not allow the total truck weight to allows the total truck weight to increase, but it does not allow the axle loads to go over the current limits. This is again reinforcing the point for residential streets that we need to be able to fund and do preservation seal coats on them, which is our preventative measure for dealing with the environmental exposure that primarily fails most of our residential streets. So we then looked at the waste facility access road. We looked at the inbound lanes. That's when the trucks are coming in. We assumed that they were coming in at legal axle loads, fully loaded. And we saw about a 5% reduction in life on the inbound lane of the waste facility road, and about a 13% reduction in life with the 2,000-pound NGV tank. And on the outbound lanes, trucks are leaving the landfill empty, and those are failing by aging, and that didn't change with this. So some increase in damage on the inbound lanes, no change on the outbound lanes. Next, please. So then we converted those into life cycle cost analysis estimates. We looked at 1%, the maximum damage we saw across all of our cases, and used that conservative number to do a life cycle cost analysis. We took that and used a 10-year period to look at the change across the state. The results were pretty similar from 2020 to 2050. We took some statewide spending on pavements estimates done from the California Transportation Asset Management Plan estimate for state highway spending on pavement, as shown on the top. And then we had two sources of estimates for local road spending on pavement, one from the California statewide local roads and Streets and Roads Needs Assessment in 2018, and a second assessment from that state transportation asset management. Those were pretty close to each other. So we used both those numbers. Next slide, please. So overall cost results from the pavement damage, we projected annual cost increases in 2018 dollars for that maximum 1% increase in pavement damage of, well, 0 to 1% of 0 to 21 million per year for the state highway network and 0 to 33 million for the local roads network. And then using the results from Miguel Heyer's analysis, most of those costs are likely to incur on the local roads networks where we expect the highest implementation of ZEV and the highest current vehicle miles traveled, which are the counties that are shown here. This is where most of the trucks are operating. We believe that improved pavement construction quality, design, management, and materials over the next 10 to 30 years to 2030 and 2050 are likely to compensate for that expected maximum 1% increase in cost from the alternative fuel trucks on both the state and local networks. I'll put in a plug. We believe that is through both improved materials, improved pavement management, better funding through SB1, and improved knowledge on the part of local forces, partly through ITS's efforts, SB1 funded efforts through the City and County Pavement Improvement Center and our training program. For the waste facility access road, we expect a change in pavement cracking life for the natural gas vehicles to be about 0 to 15%, or rounding a bit, 15% on the inbound, 0 on the outbound. It will vary with the pavement structure, the size of the trucks, etc. Maybe an 18% increase in life cycle overlay costs. Just strengthening those roads if it's needed with the next rehab, design it for those heavier vehicles on the inbound lane. And that's kind of a one-time cost that should be quite a bit less than 18%, because the asphalt costs in a pavement rehabilitation project are usually, the actual extra material is only about 50-60% of the project cost for a local government project, more order of magnitude. Next, please. Overall greenhouse gas results from the pavement damage, again, using that 1% increase per lane mile times the number of lane miles in each sector of the network. For the state highways, it's really the outside lanes that carry the trucks. The inner lanes shouldn't have any change in damage from these alternative fuel trucks, nor alternative fuel cars. So for the state highway outside, we only use the outside lanes, and we used all lanes. We assumed all county and city roads are 2 lanes. Total estimated increase in greenhouse gas from the 1% increase in damage is about 1.15 kiloton CO2 equivalent over the 30-year period, which is about a 38 kiloton per year increase. Again, this only considers the damage for the heavier pavement damaging trucks. But again, we don't expect much, if any, damage from any of the other vehicles. So we only considered those, but that's where far more than 90% of the damage is going to come from. That's load related as opposed to aging environment related. Again, this doesn't consider that increase in pavement damage doesn't consider the lighter trucks in the statewide freight modeling. But if those lighter trucks are not included in the scope of this study or similarly being converted to alternative fuels, those are major decreases in greenhouse gas emissions, and they're not going to cause any change in pavement damage. Next, please. So to wrap up, to answer some specific questions that were asked, provide estimates of the effects on freight logistics of more alternative fuel trucks operating on the network. Increased numbers of AFT are expected to occur. Those, as Marshall was talking about, this is primarily in the short haul and medium duty types according to the pathways that were analyzed in this project. As he noted, the zero emissions by 2045 means that the long hauls have to be 100% alternative fuel as well. We didn't analyze that. The scenarios for long hauls range from not much implementation by 2050 to pretty significant, but still far less than the short haul and the medium duty trucks. Range issues exist for the battery electrics and the fuel cell long haul trucks in 2030. Those get better to 2050. And as I mentioned, Marshall mentioned, by 2050, an estimated 25 to 70% of long haul trucks are fuel cell or battery electric. According to the scenarios analyzed. Most of those are expected in the 11 counties with the greatest freight traffic, which are primarily urban, or they're more rural counties that have major freight corridors. Second question, provide an estimate of the weight restrictions problems for local and state government bridges caused by all trucks operating with additional gross vehicle weight of 500 to 2,000 pounds. Difficult to answer even at the first order conceptual level, as we talked about. Bridge damage models just aren't there. Potentially allowing axle increases to 2,000 pounds is not a major issue on modern bridges. Most of the issues were called out in that study to occur on already inadequate bridges, most of which are owned by local government. So this really needs more attention on a case-by-case basis, but the major risk is to the already inadequate bridges, the vast majority of which are owned by local government. Next, please. Provide an estimate of additional damage to local and state government pavements caused by AFT operating with an additional gross weight of 500 to 2,000 pounds. We found minimal damage to both the local and state pavements. The damage will vary according to the pavement structure and the implementation scenario, and it's very much predicated on the estimates of speed of implementation to 2030 and 2050, and very completely dependent on the estimates of what the axle weights are going to be for each of those technologies and for each truck type in 2030 and 2050. Again, the reason we saw so little damage is that while the trucks are heavy for the next 10 years, we see the projection was very little implementation. And then as you move towards 2050, as implementation really takes off, the trucks are getting lighter. And again, the effects are also diluted by the trailer axles, which we don't really expect to change. And AB 2061, a key part is that it doesn't increase axle load limits. For the natural gas technology, we didn't see, it was not projected that that would change. The market penetration was pretty constant and not that big across the projections. Residential streets are still going to fail by aging, not the increased weight of the waste vehicle loading, of the loading from the waste vehicles. A little bit of increase on the inbound lanes of the waste haul roads. That can be dealt with by just thickening those pavements up a little bit. Next, please. Provide an estimate of the change in greenhouse gas emissions from implementing vehicle fleet changes that consider wheel-to-well emissions and maintenance and rehab. I'll just sum it up without reading all through it. I know we're over the time. The overall transportation sector in 2016 is 175,000 kilotons. To cut to the bottom line, using Marshall's numbers for the vehicle emissions, say reductions in greenhouse gas, and our calculations of the increases from increased pavement damage, the reductions from the vehicles are 60 to 900 times greater than what we could see in terms of increases because of pavement damage. So bottom line was, if we actually go to the last slide here, overall recommendation to achieve these large reductions while still considering changes in agency costs, we don't see a major impediment from increased pavement damage. That needs to be monitored. The assumptions of this study need to be monitored to see how they play out. but that's the overall recommendation. We definitely need better models for bridge damage. We need to continue to check the assumptions of this study and periodically improve the data and the models. We have no models. We have good models for how road roughness impacts diesel and gasoline vehicle fuel consumption on the order of 0 to 5% changes in fuel consumption. We have no idea at this point how road roughness changes the energy use of the alternative fuel trucks, and we have no idea what road roughness does to the life of their propulsion systems. Develop improved models for greenhouse gas emissions for the truck manufacturer, which was not considered here. Differences in truck manufacture. And if we start going to semi-autonomous and autonomous truck operations, that will also change some of the characteristics of pavement damage and also the greenhouse gas reductions from the truck's propulsion. Next slide. And I think that's it. Okay, Mike, I hand it back to you. We went a bit over there.
Hey, thanks, John, and thanks, Marshall, for taking us through that very complex. Your team did some like good work to tease out some complex questions there. So we've been answering questions as the webinar has proceeded, so you can look up those answers in the Q&A. I did want to just try to squeeze one question in before we close here. Maybe it's more for Marshall, but I'll open up to both of you. So, it sounds like from your conclusions that this increase in gross vehicle weight limits is really not having much of an impact in terms of pavement damage and costs. So given that, and Marshall, given some of your assumptions about the technology improvements, bringing down the weights of these alternative fuel vehicles, do you see vehicle weight limits as being an impediment to zero emission vehicle adoption? So if the state is trying to kind of remove barriers to adopting zero emission trucks, is weight limits something that needs more focus in the future, or are we seeing that because the technology is getting better, maybe it's just not going to be an issue, if that makes sense?
Yeah, by far the major issue I see is in the long haul sector. To get a significant range for long haul trucks, batteries would have to be large and very heavy and cut into payload enough so that there's really large concerns over whether you could have even a 500-mile range truck. That fleets we've talked to are not at all happy with the thought of only a 300-mile long-haul truck. Maybe they change how they operate over the next 30 years or 20 to 30 years. So for long-haul battery electric trucks have a significant problem with weight. Fuel cell, we think, probably won't. Obviously, early fuel cell trucks are a little bit heavier, but we do expect that weight to come down. So it's really in the long haul sector with battery electric. That's the main reason why we project vast majority of market penetration due to fuel cells rather than battery electric.
Gotcha.
Marshall, kind of following up on one of the questions, it's in the questions and answers, and I don't remember the answer. If the ranges are less and I don't see that big an impact on the payloads, because most of these trucks are volume constrained on our network rather than weight constrained, as we saw in our axle load spectra. So it's really the length and width of the truck for many of the cases that's controlling. But there's a comment that LA County has estimated that 1.7 E trucks are needed to replace one diesel truck. I don't know if that's medium duty, long haul, short haul, but I don't think that we looked at any trade-offs, and we'd have to look deeper into why those would occur. Any thoughts on that and how you incorporated that at all?
Yeah, we did not incorporate that. I was actually part of a study. I don't know if this comes from there, but we just finished this study last year that looked at port trucks. So this would be what we would call short haul drayage, but that would be included in short haul. And for port trucks, the idea was that in early like 2025 and possibly even 2030, the range might be short enough such that you would not be able to complete all of the routes that a diesel truck could, and you would need extra short haul trucks, battery electric, for example. We assumed mostly battery electric early, and so you would need extra trucks to do all the routes. I think that will probably not be an issue, certainly past 2030, maybe 2035 or so. We expect that ranges for battery electric trucks could probably easily handle the routes necessary for most short haul trucks. And so this 1.7 may be near term, that could be an issue. Longer term, I don't see that factor being anywhere near that high, and possibly as low as 1.
One other, I mean, projecting the future, there's always just a little bit of uncertainty. You know, a lot of the questions also have to do with what are we hauling 10, 15, 20, 25 years from now, just freight patterns and changes in the economy. So the farther you get out, the more uncertainty. The general trend, at least which was the scope of our study, is that we did not explicitly consider having to use more trucks. But over the long haul, as Marshall was saying, that expect that effect to diminish across the, you know, the general truck fleet. Then I think kind of summarizing what you say there, right, Marshall?
Great.
Right.
Well, thanks very much to you both. So we're out of time. I did want to, you know, thank you both for presenting and thank everyone for attending the webinar. For our participants, you will see a quick survey when you log off to share your thoughts on today's presentation. And you'll be getting a follow-up email tomorrow when the recording is available on the UCITS website. And finally, I'll just leave you with this slide. We do have another upcoming webinar on February 25th on the effects of COVID-19 on mobility of vulnerable populations. So we hope you will join us for that as well. Thanks very much, everyone. Have a good day.
Thank you.
Thank you.